Is on the Arrhenius equation, which allows us to calculate activation energy for chemical reactions. Here's the Arrhenius equation. As you can see, this equation relates K, the rate constant, to the activation energy and specifically to the temperature of a reaction. You will recall that as we increase the temperature of a reaction, the rate of the reaction increases, which also increases the value of the rate constant. You would also recall that as we lower the activation energy for a chemical reaction, that also increases the rate of the reaction, which also increases the value of K. What this equation shows us is the temperature dependence of the rate constant and also its dependence on the activation energy of the reaction. There are three forms of this equation that you are supposed to be familiar with. The first one is the main one that I showed you. Here, you just need to know the main components of the equation and what they tell us. In the second one, we have applied log rules and we get a linear version of that equation where we would be using that equation to draw a graph and then calculate activation energy using the graph. The graph is called the Arrhenius plot. And then in our last version, we are to use this equation where you'll be given two K values at two different temperatures and then calculate activation energy algebraically. You don't need to know how we got from 1 to 2 to 3. Here's the main equation. The two major components that you need to know here are A and then E to the negative EA over RT. A is known as the Arrhenius constant, also known as the pre-exponential factor. And essentially, when you solve for A, it gives us the number of molecular collisions per second with proper orientation. We can also rephrase that as frequency of collisions with proper orientation. This is a constant because we have no control over the collisions with proper orientation. The second part of this, e to the negative EA over RT, tells us the probability of successful collisions. In other words, collisions with energy that is equal to or greater than activation energy. This is something that I can affect. I can reduce the activation energy, or I can increase the temperature in a reaction, and that can increase this component of this equation. If we apply log rules to that equation, we get this linear version, which is in the form of an equation of a line. You can see here, y is equal to ln k, and m here is negative EA over r. X is 1 over t, and your y-intercept is ln a. This equation is quite handy because we can use this equation to draw a graph, which is known as the Arrhenius plot, and the graph would always obviously be y versus x, ln k versus 1 over t, and the graph would be sloping downwards in a constant manner here. And what you would be required to do is to use this graph to calculate activation energy. How do we do that? You have to calculate slope. If you look at this equation, m equals negative EA over r, m being slope. If I can find the slope of the graph, if I have the value of r, which we do, we can rearrange this equation and calculate activation energy. Activation energy would then be negative m times r. Remember here, your slope is going to be a negative number, which means your slope here is going to be negative. That's important because once you solve this, activation energy will be positive. Activation energy is always positive. It's never negative. Lastly, activation energy is expressed in kilojoules per mole. When you solve this equation right here, your answer for activation energy is going to be in joules per mole. You are going to have to divide that by 1,000 to convert it into kilojoules per mole. Here's a worked example. In this case, you're given 5 K values at 5 different temperatures. Here are your temperatures, and your job here is to plot the graph, the Arrhenius plot, and then use that to calculate activation energy. Before you plot the graph, you must convert the K to ln K, and then you must also convert your temperature to 1 over T because the Arrhenius plot is ln K versus 1 over T. Once you do that, you can plot the graph. This would be worst case scenario on a test or an exam where they ask you to actually plot this graph. Once you plot the graph, you will then calculate the slope by rise over run, and here's your slope. Then you will rearrange that equation that we saw on the last slide, and you would calculate activation energy. Keep in mind, activation energy here will be in joules per mole. You would have to take that at the end and convert it into kilojoules per mole. Keep in mind, activation energy is always positive. You can also calculate activation energy using the algebraic form. Here, you'd be given 2K values at 2 different temperatures. You can obviously isolate for EA here, or you can solve this part by part and then just calculate activation energy. If you wanted to rearrange this for activation energy would be ln K1 over K2 times R divided by 1 over T2 minus 1 over T1. Let's take a look at a worked example. Here's a question here where your temperatures are given at 25 degrees and 270 degrees, and then your K values are given accordingly. You would, obviously the first thing you would have to do is to convert your temperatures to Kelvin. The temperature has to be in Kelvin. If you are an IB, you don't have to put the 15 here. You just add 273 to your Celsius temperatures, and that'll give you the temperatures. From that point on, you just plug those numbers in directly into the equation and solve for activation energy. Once again, keep in mind that activation energy must be in kilojoules per mole. When you solve this, your answer will be in joules per mole. The last thing you have to do is to be able to calculate the value of the Arrhenius constant, A. A, if you recall from that last equation, which was ln K, negative EA over R times 1 over T plus ln A. Ln A was your y-intercept. So in this case, my y-intercept is right there. It's given to me as 23.85. To calculate the value of A using the y-intercept, it's e to the intercept, and you end up with this value of A.